All right. You've probably heard about DeepSeek. Everyone has, for some reason. It is kind of crazy. So I wanted to cover it, and I mainly wanted to cover this paper because it's how does DeepSeek actually do it? R1, I don't think is that interesting. R1 is actually kind of built into this paper a little bit. This is mainly how they get this thing so cheap. And on that point, there's a lot of talk about, oh, this thing is super cheap compared to all the models that are trained right now. I think there is some truth to that. I do think they make it a lot cheaper than current models because current models are trained, at least, I mean, I don't know how they're trained because I don't work at like Meta or Google or OpenAI, but they are probably trained using a more naive algorithm. Here, they make the algorithm or the algorithms they use very, very, very computationally good compared to like naive PyTorch. So I do think it is cheaper, but the amount that is being thrown around, there's no way it's that. Also, the amount they say in the paper is only how much it takes to train from beginning to end, not how much the experiments take. So I think there is some truth. I don't think it's as large in magnitude as people are claiming. So yeah, that is what I want to say about that. But it's mainly good because they do a lot of cool tricks. Usually I don't really like to cover papers beginning to end, but this one I mainly am because they do a lot of really interesting tricks in here that I think are worth covering. But I'm going to go over the main ideas. And there are some details that I'm going to leave out mainly because it's like you could just go through and kind of read those details, but there's so many good details in here that it would just be me reading the paper at that point. I'm going to break it into three parts, kind of like the architecture changes, the hardware and tricks they use, and then at the end kind of talk about the results a little bit. I mean, obviously they get state of the art because everyone gets state of the art. So yeah, that is that. Yeah, so let's talk about the results. Also, I don't know why, or not results. Also, I don't know why everybody's like, oh no, they're stealing our data. They're from China. They must be stealing our data. OpenAI also steals your data, by the way, using ChatGPT. So yeah, I don't know what the scare about that is. Besides that, all right, let's actually get into the details. Yeah, this paper is massive. I'm just going to go through it kind of. I'm going to go through the architecture first. So they make a lot of changes to make this very, very, very efficient to train compared to the normal transformer. So the normal transformer looks exactly like this. And they basically chained the attention to this. They use the same attention mechanism, but the projections they have are different. And in attention, you usually have this KV cache. And this KV cache is what you use during inference. And this KV cache is very large, and it grows linearly with respect to the sequence length. So this grows linearly with respect to the sequence length in terms of memory. Now, what they do is they compress this, so it still grows linearly, but it grows linearly slower. And we'll see how they do that. But they use projections to make this smaller. And if you can half this size, that means you can store double the amount of tokens, theoretically. So that's one optimization they make. They also do a lot of mixture of experts, and I'm going to talk about that whenever I get to it. But they change these feed-forward layers with mixture of experts, which is a way of scaling this to a lot of parameters without having to actually compute those, without actually using all those parameters. So that means you can have a ton of parameters, but the compute needed to utilize those parameters is much, much smaller. I forget how large they scale this, but the amount of parameters you actually have to use while you're doing computations on the GPU is much smaller. So you can actually make larger models with the same amount of compute. So those are the two big things they do here. So and then they also do multi-token prediction, which is what I'll talk about later. So multi-head latent attention. That's the first optimization they do that I was talking about, where they compress this KV cache. So they don't do anything with the attention itself. The attention is the same. It's how do you get the query key value projections to be smaller. So normally what you would do is you would have your token here, and you would project this to your queries. So this token is of dimension D. You would project this to your queries of dimension D, your keys of dimension D, and your values of dimension D. So queries, keys, and values. And then you do attention with these here. Now, for the KV cache, every time you have a new token in your sequence, you need to store both the queries and the keys, or you need to store both the keys and the values, not queries and keys. So every time you have a new token in your sequence, you increase your memory by 2D. You just need to store these. What they do is they make a mechanism that allows you to store a lot less parameters. It's on the order of just D instead. So how do they do that? I'll leave that there. So it's this here, this diagram here I drew out. I'll break it down. They also have a diagram up here, but I didn't like the circles as much. Just my bias towards my diagrams, I guess. But it's this big mess here. So I'll just break it down here instead of talking through the formulas. It's the same as the formulas. So what we do is we start with our token of dimension D here. And what we're going to do with our token is we are going to do a projection here. This projection is a normal projection, or this projection is kind of what you can think of as the key and value projection, except it's a down projection. So this goes from dimension D, so whatever our current token dimension is, and it down projects it to dimension DC. And DC is going to be this compressed representation that represents both the keys and the values in this one token. So instead of projecting our input token to keys and values, we're doing one projection, which will be used for the keys and values. So that means we just have to cache this, as well as this token up here, which I'll get to in a sec. But you just have to cache this token, which is less than D, actually. So instead of it being 2D, it's just of size DC, where DC is less than D. So it's actually less than half the size you're storing. So what you do with this token is you then project this to the keys and the values. So whenever you do attention, you usually have these rope embeddings that you add. So I have this over here. To do positional encoding, you can either add that to the original sequence, or you can apply rope to your queries and your keys. And I'm going to show how they add rope in a second, but usually what you do is you just add the rope parameters, the rope values to your queries and your keys independently. I'm not going to get into rope because that's long, but basically it's just positional encodings you're adding to your queries and the keys so that they know the relative position of each other. So query knows, or this key knows, oh, I'm 5 positions away from this query or something like that. So that's what we have here. So that's up here. So you have this token here. You project this token, this compressed representation of our keys and the values, to the keys and the values. So you do an up projection to dimension D by N. So this token here of dimension DC is projected to dimension DN or DH by HN. And what this represents is you're doing an up projection to all the heads and all the head dimensions. So you're taking your one projection and you're projecting it up to this token, which is then split into multiple heads. So that's what this is here. This one token projected to the number of heads and the head dimension here. I drew it spaced out instead of collected together, but you're just projecting it to a really high dimension and then breaking it up into your number of heads as you do in normal attention. This projection here does the same, except with the queries, or with the values here. So we have these two sets of parameters, and then you can do normal attention with them, except we have to add the rope parameters. We have to add the rope embeddings. So to do that, they take the original embeddings, and I'll explain why they take the original in a sec. I actually have the note right here in yellow. So they take the original embedding, and they have this down projection here, and this down projection creates this one token used as your rope embedding, and you apply this, you then concatenate this token. So this is a down projection here. You concatenate this token to every one of your heads here. So it's just one token, and you're concatenating it with every token here. So that's what you see here. So project to this compressed representation, take this then up project this compressed representation to keys and values, take our compressed rope take our rope representation and concatenate that with our keys. So that's the keys and the values. So all we have to do is store this and this here. These are the two things we have to store as our cache, where the dimensions here are really small. So instead of storing 2D parameters every time, you store DHR plus DC parameters, where this is probably less than D. So less than half the parameters you're storing. We also have to create the queries. So to create the queries, we take our original embedding, and since we don't have to cache, it doesn't really matter what you do to this. So what they do, but they allow you to also make a compressed representation of the queries. So they down project this to D prime C, so like you do here, and then they up project this to the rope embeddings. Oh, that's down here, to the rope embeddings and to the query embeddings. So they down project and then they up project to the queries and the rope. And then they concatenate them like you do with the keys. So it's basically the same thing as the keys, except one thing is the rope parameters actually come from here. So the rope parameters are coming from the compressed representation of the queries, while the rope parameters for the keys do not. And that's because you have to do, I forget exactly what extension strategy they use, but the extension strategy is a lot easier because you have this decoupled rope embedding, and they only do the length extension. So like if you already have a pre-trained model of size 32,000 and you want to extend it to say 128,000 tokens, they only do the extension using the keys. And since the keys are decoupled, it makes it easy to work with. But if they weren't decoupled, it would make it a lot more difficult to do that. So that's just a note I made over here. I forget exactly what length extension strategy they use, but they do use one so that you can pre-train at a very cheap cost for a small sequence and then extend it. So once you have your queries concatenated, your keys concatenated, and your values, you can then you then just do normal attention here. So that's the idea. It's mainly you create these compressed representations here and only store this compressed representation so that it's a lot, like you store a lot less parameters as you're doing inference. That's the idea. So inference is a lot cheaper for this model than other models, token-wise, assuming they use the same number of parameters. I think this one is, this part it isn't terrible. It's just they compress it and yeah, they store that compressed representation, but it's a really smart way of doing it. So I'm a big fan of this. Yeah, moving on. Yeah, so normal attention here, that they do. Normal multi-head attention, nothing out of the ordinary with this. Yeah, normal output projection. So DeepSeek-Mo, they wrote a paper on this before, called DeepSeek-Mo, which has more details in it, but they go over it pretty thoroughly in here. They mainly have this Mo architecture that they design, and there's a few cool tricks they use in it. So whenever you're doing Mo, so I'll go over Mo kind of from the beginning. So Mo, you essentially have a token, and what you do with this token is in a normal feed-forward network, you will throw this through a feed-forward network. So you have your up projection, you have your activation here, and then you have your down projection. You feed it through the feed-forward network, and you get this output representation here. Of course, with a residual connection like that. So yeah, this is your normal feed-forward network that you have. With Mo, the idea is we have a token here, and the idea is you can have multiple feed-forward layers that are smaller. So let's take this here, because these are quite large in parameter count. So let's take this and let's create a few of them. Got 2. Let's add another one, 3. And the idea is you can have experts which specialize in doing something. So maybe one is good at looking at a certain representation, or maybe one stores certain facts or something like that. The idea is you can use the original idea is you can use Mo for this. So this token says, oh, I want to go here and I want to retrieve some facts here. And now I'm updated with this representation. So now I have information of, I don't know, geography or something. Well, this one may be math, and it may help with that. So that was the original idea. But the nice part is you can scale this a lot larger. So let's say these were actually the same amount of parameters as an original feed-forward network. Here, we're using the same number of parameters. The number of active parameters are just this feed-forward layer, but the number of parameters total is 3 times the amount we had before. So theoretically, you should be able to store a lot more information in your network. And you can scale this to really large amounts and only have a limited number of active compute that you're using, while the number of parameters is massive. You couldn't do this with the normal feed-forward layer because you can't store this in memory. But since you split it up, you can. Now, this does come with a lot of downsides. For example, how do you route? And even if you know how to route, let's say this expert here kind of was originally useless, then you only get gradient signal for this set of parameters here, and this set of parameters will likely only be updated. Like if this set of parameters was originally completely useless, the router probably isn't going to say, oh yeah, I should use this completely useless feed-forward network. So you run into issues where certain experts aren't used, and there are problems with that. So they fix that, and they have a method to fix that and mitigate issues that are usually found whenever you try to fix that issue. So let's just talk about it. So there's there's I guess 3 parts to this. So here, this is our updated representation. U is our input, and we have 3 parts. So this is just the skip connection. It's just a skip connection. You always have a skip connection. This here is a static set of feed forward, or this here is what they call a shared set of feed forward layers. So every token is passed through these. So intuitively, maybe there's a certain set of information that every token should be updated with. So that's what you have here. Though you can just think of this as, there is a every token will be sent through the same feed forward network and the specialized feed forward network. If this was just a weight multiplication, then this sum would kind of be useless because you can sum all the all the matrix multiplications into one weight. But since this is an MLP, they mentioned just like the original MLP you would use in a neural network, then you can't do that. So that's something I initially thought. These are MLPs. They're not just weight matrix multiplications. This is the interesting part here. This is the mixture of experts part. So this has 2 parts to it. What you're doing is you have n sub r number of experts, so whatever that may be, and you're summing over every expert. So you're not summing over the active experts, you're summing over every expert. So every expert will have a weight corresponding to it, and that comes from your router, and every expert will also have the output of said expert with the input sent through it. So how do we compute this gated output? First, you have this multiplication here. So they use S sub I. It's a lot easier for me to think about, this is a projection taking the dimension to every expert, and then you apply a sigmoid to it. Note that they apply a sigmoid to it. So essentially you have a token here of size D, and you up project this to your number of experts, and then you apply sigmoid to every part of these. So this is your router, and this says which expert, or this is the probability of going to every expert, or the weight going to every expert, however you want to think about it. So that's this value here. And they use a sigmoid, so they don't have relationships between experts, which is what you usually see with the softmax. They use a sigmoid, so they're independent experts here. Now, using this weight here, what they do is they take the top K experts. This is for the ith token. So for a token, they take the top K experts. Maybe that's like 2 or something like that. I think they use 8. I think they use 8 experts. So top 8. And they zero out the probability. They zero out the token or the probabilities that are not in this top 8 expert set, and they keep the value if it is in the top 8 expert set, and that's our gate output. So that's what I was saying here. Here they normalize it. So if we just take the gate output, then we're going to have values like they aren't going to sum to 1. So you have issues here with the magnitude, like you have issues here with the sum, because some sums are going to be larger than other sums, like the magnitude that you have, the sum of the weights is going to be larger for some tokens than others. So you run into this magnitude issue where some tokens are higher than others in terms of the magnitude. And to get around that, you basically take all the non-zero weights and you divide by the sum of those weights. This is summing over every weight, but since there's zeros, you're just summing over the active weights. So you're just normalizing this so that the weight of every token sums to 1. So that's what this is here. And you send all the experts, or you send this token to every expert, but since only 8 of them are non-zero, most of the experts are zeroed out. So that's what's happening here. Pretty straightforward, normal Mo. And I have that drawn out over here. You have your token. It is sent to this router. This router produces a set of weights, 1 for every token, using this sigmoid. You then select the top K. The top K are then, the expert. You send the token through the top K experts. So in this case, K is equal to 2. And you do this reweighting of your weights. So you multiply the output of said expert by the weight, by the reweighted weight. So these weights add up to 1. And then you sum all the outputs of the experts together. And these are your shared experts and the residual. So that's what you have here. Mo. So that is just normal Mo, but this will run into problems. Like this will run into I forget exactly what the name of the problem is, but whenever you have experts that aren't, that information isn't sent to. Like if this sigmoid is just 0.1 for some token or for some expert every time, then it's not going to get information sent to it. So how do you fix that? So an easy way to fix that is to add this auxiliary loss here. Complementary sequence-wise auxiliary loss. So we're going to add an auxiliary loss that penalizes tokens being sent to experts too much. So let's just break down all these equations here. So this value here, it basically represents the normalized expert score. So I said here, this is basically how much more preferred is this expert over the other experts. This is the score over all the experts, and this is the score of an expert. So this is the output score, and you're basically normalizing by the other expert scores. So this is going to be higher if it's a higher score and lower if it's a lower score. But it's how does it compare to all the other scores, essentially. This is just this value summed over or averaged over the sequence. So this value here is, I like to think of it as like the expert preference. So the average preference of this expert over the other experts. So that's PI. FI here is this value here. So this is the top K weights here. So the weights that are active, the active experts. This is the sum over the entire sequence. And you're basically averaging over the sequence and the number of experts that you're selecting here. So this is kind of this is the weight and this is the preference. So intuitively, your loss is going to be higher if an expert is more preferred. So because this is just a direct loss. So this is, I think once it's broken down, it's kind of intuitive. If this is your preference here for an expert, for expert I, and you're summing over all experts, and this is kind of the weight of that expert, which is higher if some of the weights of that expert are higher, then this intuitively this will penalize experts for being preferred too much. This is an easy way to do that, but it's not a good way. You can imagine if you optimize this too much. Well, first off, if you optimize this too much, it won't optimize the next token prediction that you're trying to do, which is what you're actually trying to optimize. Additionally, you kind of will get you'll get this smoothing effect where a good optimum for this is every expert is sent tokens the same. So that way, it kind of minimizes this loss. That's a good way to minimize it. Just every expert gets the same weight. So they say this isn't a very good way of doing it. They add this a little bit. They add this to prevent extreme imbalance with any single sequence and employ a complementary sequence line. Yeah. So they add this for with a really, really small weight. I think it's like 0.0001 or something like that. It's something really small to prevent extreme imbalance. But they have something smarter that does not require loss. So that's awesome because your model can focus on optimizing what's important, the next token prediction. And it works better because it doesn't have to optimize that loss, and it's pretty easy to implement. So it's really simple. Basically, we have our sigmoid weight here for every expert. And the sigmoid weight is going to be added. It's going to have this bias here. So all we're doing is for every weight for every expert, this is the routing weight. We're going to add a bias here. And you only add that for So you add a bias, and the bias is it's added to every expert, even the experts that aren't selected, so that you can balance it out. So intuitively, the higher the bias, the more likely this expert is going to be selected. And whenever you're doing backprop, the backwards weight is since this is just an addition, it's going to use this. So what they say here is we pioneer an auxiliary loss-free balancing strategy to ensure load balance. To be specific, we introduce a bias term, BI, for every expert and add it to the corresponding affinity scores to determine the top K routing. So how do you optimize this? How do you define this bias? So they say at the end of each step, we will decrease the bias term by gamma if its corresponding expert is overloaded, and increase it by gamma if its corresponding expert is underloaded, where gamma is a hyperparameter called the bias update speed. And they mention overloaded and underloading. They mention that, and that's basically if there's a certain number of tokens being sent to an expert. Like if there's a ton of expert, they define some value. I forget exactly what the value is, but if there a certain number of tokens are being sent to that expert, then it'll be overloaded. And say if 0 were sent to that expert, then it's underloaded. So that's what this is here. Increase gamma, or decrease gamma if there are too many tokens being sent to an expert, and increase it if there are not enough. So, and this works quite well. I'll show later that this actually it doesn't result in a smoothing effect, or it may, but it's a lot less than the hard loss function that you're using. And that's nice because you can have experts that actually specialize in things, experts that are important. It's just not overwhelmingly important. So that is that part. I think this part's pretty cool. And then they do this here, which is a multi-token prediction. And the idea with multi-token prediction initially was, we can speed up the model during inference if we have a token, say we input a token into our model and we have it predict the next 2 tokens or the next 3 tokens, then we can speed up the model. They, on the other hand, don't do next token prediction for that. They say, well, we can do next token prediction, and that can speed up the model. But what we want to do is we want to do next token prediction so that the model can learn a richer embedding for our token. Because intuitively, if you have a token that needs to predict the next 2 tokens, so if you have a word that needs to predict the next 2 words, it should be a lot richer with information than if it just needed to predict the next 1 word. It has information for how to predict the next 2. And kind of thinking about that, there isn't an obvious reason why. Just thinking about that, it does make sense for this token that has to predict the next 2 tokens to be better at predicting the next word in a sequence, or predicting a sequence of words. Because let's say it needs to predict the next 2 words, it may decrease the probability of a word if it were to just predict the next word. So it's informed of more of the future of a sequence than just the immediate next word that it has to predict. So they don't use this for speeding up the model during inference. They just use this to enrich the information of a word or of a token that's doing multi-token prediction, but they still use it just for next token prediction. So how do they do this? Let's just break down the diagram. It's not complicated. They take the input set of tokens here and they throw it through a transformer block. So this is basically their big backbone that they use. This is the biggest part here. It's pretty much where all your parameters are going. Then what you do is you throw it through the output head and you get your normal next token prediction loss. So that's what you have here. This is just normal what you have. Then what they do, I'm going to erase all this mess here, is they shift the tokens by 1, and we want the model to now take these embeddings here, so before the output head. So these embeddings should be used to predict the next token, but we want to use them one more time to predict not the next token, but the next token. So we're going to utilize token 1 to predict token 3. And what they do is they take these latents here, and they normalize them, and they take the latents of the embedded form of the tokens shifted by 1 here. So whatever the next word is, and they embed it here, and they concatenate them along the dimension axis. I think I have a drawing. Yeah, I have no, I don't. So basically you take your embeddings and you concatenate them together along the dimension axis here. And then what you do is you use this embedding, which has information. So this is the latent part of the predicted next token and the latent of the actual next token. And you use this to predict token 3. So this will be token 2 prediction, and this will be token 2 actual, and you concatenate these two together and you use that to make a prediction for token 3. So you send this through a single transformer block. That's all you do, and you then get your output for token 3 here. So it's taking these predictions, it's taking the pre-projection predictions from your model, concatenating it with these embeddings here for the next word to kind of enrich the representation of this output, like enrich it with some details of what the actual next word is, and use that to predict the next word. And you do the same. You take these latents here, you take the next words, the words that you should have predicted here, you concatenate them together along the dimension, and you use that to predict the next word. So 3 words in the future. And they note that they share the embedding layers and the heads here, because those are very large in terms of parameter count. There are some notes down here that I want to talk about. I do. So, I do have a diagram. So you take the token at time t, you embed it, you then get this latent representation, you throw this through your massive backbone transformer, which is what you're going to do, what you're going to use for actual next token prediction, and you get an output. And you project this output to get your output prediction. So that's just your normal next word prediction. So for the next word, you take the actual next word, you embed it, and you get your hidden representation. You then concatenate the hidden representation of the pre-projection for the predicted next word and the embedded representation of the actual next word. You concatenate them. You then do a projection, you get your normal dimension. So this combines it in some way. You throw it through a single transformer layer and you get your output for the next prediction here. So that is next token prediction. There are some notes here that they make about the routing for mixture of experts and multi-token prediction. So tokens are sent to at most m nodes. So they say here, in short, like the device limiting routing using in DeepSeek-V2 and V3, we also use a restricted routing mechanism to limit communication costs during training. In short, we ensure each token is sent to at most m nodes, which are selected according to the sum of the highest k are. So k is the number of experts and m is the number of nodes, affinity scores of the experts distributed on each node. basically, you don't want your experts going all over the place, so they're going to use a ton of nodes to train this thing, compute nodes. So this kind of limits that. And no token dropping. They mention that due to the effective load balancing strategy, DeepSeek keeps a good load balancing during its full training. Therefore, DeepSeek-V3 does not drop any tokens during training. So that's a good thing, because if you have a token that does not go through your mixture of experts, then it's like it needs to be updated in some way. So just skipping that communication isn't as good as going through or skipping that computation. So it doesn't, none of the tokens skip. They are at least sent to an expert. Multi-token prediction here, which we talked about above. They do only do a next token prediction. So they mention here they have D sequential modules to predict D additional tokens. They make D equal to 1. So they do next token prediction and then next token prediction. And during inference, they remove the head of the second prediction. So they're literally only using it to enrich the representation of the next token prediction. And they do find it does help out. It does help out. And they pretty much optimize it the same. So negative log likelihood here, and they weigh it by some value. They mention the value down below. And they say here, our MTP strategy, multi-token prediction, mainly aims to improve the performance of the main model. So during inference, we can directly discard MTP modules, and the main model can function independently and normally. So those are the 3 architecture changes that they make, the 3 cool architecture changes that they make. The first one is we can take attention, we can compute the keys and the values in this compressed state so that you only have to store on the order a much smaller representation of the keys and the values. It's a compressed representation. So that's what they do here. Here, they make it Mo, and they make Mo efficient, and then they have multi-token prediction. Those are the architecture changes. Now, let's get into the second part here, which is training and all the cool tricks they use. So I am not the best with this because I do not have 2,000 GPUs. So I only know so much. I'm going to explain the parts that how everything works to the best of my understanding with this. I don't have 2,000 GPUs, so I can't actually see, does this make sense? I'm going to go test it. So they basically, this is where the efficiency comes from. They already have a lot of efficiency above. They have the efficiency with the tension, so you can get more out of the parameters or out of the compute you're using. They have Mo, so you can make the most out of the feed forward layers and make a model with a lot of parameters without having to actually compute all those parameters. And then next token prediction to get the most out of the data that they have. Now they want to get the most out of the compute that they have. So I'll just talk through this, I guess, one by one. There are a few parts that are really cool. So, and it's mainly, this first part is this training framework. So they mention these multiple parallelism strategies. They mention a 16-way pipeline parallel. They do this cool parallelism strategy that they do it in this specific way to maximize the compute they're using. So 16-way pipeline parallelism, which is pipeline parallelism is one model on multiple GPUs. So 16 GPUs and you have one model on that. 64-way expert parallelism, which they mentioned spans 8 nodes. So every node is going to be a cluster of 8 H100 GPUs. So they have a 64-way expert parallelism on that. So they put all their experts on 64 GPUs, which spans 8 nodes. And then they use data parallelism. So data parallelism is the normal parallelism where you copy a model to in a normal case, you would copy a model to a GPU to like 8 GPUs, and you would then feed forward different data on those 8 GPUs, and then accumulate the gradients to create this big batch. So you basically have the same model on multiple GPUs. You do a feed forward for all of them. You do a backward for all of them on the data, and you accumulate the gradients for all these, in some different way. But you accumulate the gradients and share them among the models. This is what you normally see, and that's data parallelism. So they do this. They combine all this together. They mentioned that they don't use any tensor parallelism. So that would be like if I wanted to do a matrix multiplication, I would shard that matrix. So a single matrix multiplication across multiple GPUs, which is very, very slow. And this is just bad. So they don't have any of that, which is good. Yeah, so the main thing that they do on their compute cluster to make this really, really efficient, or the first thing they do, is they overlap this forward and backward pass. And they mentioned there are 4 parts to that. So you have a forward pass for basically attention, you have a forward pass for your MLP, and then you have the other weird obscure things like the embedding and unembedding. Those aren't as important as the main parts, the attention and MLP. And for each of those, you have these backward passes here. And then you have these all-to-all dispatches here. And for the backward passes, they mention, you have your backward pass for your input and backward pass for the weights. And they mention, or rather they draw this diagram, and I'll walk through the diagram. I think that makes it easy to see what's going on. I'm going to erase it so I can walk through it again, because this diagram's a little scary. At least whenever I first looked at it, I'm like, what the heck is going on? But what they assume here is that there is a unit of time for a forward pass, for a backward pass with the inputs, and a backward pass with the weights. And you can do that with, you can do that because you have to send information, since you're doing this pipeline parallelism. You basically have a part of your model on one GPU, on another GPU, and another GPU. In this case, they use 8 PP, so 8 pipeline parallelism, which means you have your one model sharded on 8 GPUs, and you have to send data through those GPUs on the forward pass. So all 8 GPUs in the forward pass, and then all 8 GPUs in the backward pass. So how do you make this efficient? And that's what they do down here. Like I said, I'm not super familiar with the other methods that they mentioned down here, mainly because I don't have access to that many GPUs, but I can say that the method they have seems pretty good compared to the other methods, even though I don't know what the other methods do. So according to this one paper, which is a very big sample size, I'm kidding. But I'll walk through kind of what they do. Basically, in this example down here, they have 8 pipeline parallelism, so model sharded onto 8 devices, 8 GPUs. I think above they mentioned 16. But in this case, it's just 8. And they use 20 microbatches. They use 20 batches, which are going to be sent through this pipeline. And this pipeline represents the full forward and backward pass for these 20 microbatches. So what they do is they send this data in parallel with each other. So we're going to have 2 copies of our model on every device. We're going to have, so we have 8 devices. We're going to have 2 copies of the model. And we're basically going to have 2 different batches going on those devices. So we're going to start off here with the first time step, and they have batch 0 right here. I'm going to walk through the other side, but mainly each block over here is a time step. So we're going to start off here with batch 0, and we put batch 0 on these 2 devices here. So device 0 is going to get batch 0, and device 7 is going to get, I think it's actually batch 10 here. So batch 10. And you start off in this way because it is a lot more efficient if you have 2 batches going at the same time than if you have 1. If you only have 1, you run into these holes here, and you don't want holes because that will run into redundant compute that you're not utilizing. You can see here they don't have much redundant compute. So what we're going to do is we're going to do a forward pass. So I'm going to show you the forward pass. I'm going to call this 0 in purple. Specifically 0 in purple, just so that it's easier to see. But this is going to be the second set of data. You can see here there's batch 0 going here forward in time. I'm going to be sending batch 10. This is going to be batch 10 going forward in time. So what we do is we start off here on device 7. We're going to do a forward pass on device 7. Orange is forward. Green is backward for input. Blue is backward for weights. And double green is backward for both the input and the weights. We start off with device 7. We put our batch on device 7. We do a forward pass. We then do a forward pass on device 6, device 5, 4, 3, 2, 1, and 0. So we just do a full forward pass through all the GPUs. And you can see that after we do a single forward pass on device 7, we immediately load the second batch. So this is going to be batch 11. I'm just going to call it 1 in purple because it's more annoying to write at 11. And this will also do a forward pass here. So you immediately load this back on. So you do this full forward pass. And you can notice here in parallel, you have the forward pass of the second stream going in parallel. So this is going to be running, like batch 0 to 9 is going to be running from device 0 to device 7, and they number batch 0 to 9 here. So this is batch 0, this is batch 1, this is batch 2, this is batch 3, 4, and they have 9 all the way over here. You can see it starts on device 0 and it'll iterate to device 7 using this forward pass, and then it'll iterate back for the backward pass. Here, this starts with batch 11, or with batch 10, 11, and it goes to batch 19. They don't number these ones. So the unnumbered ones are the batch going in parallel in the opposite direction. So we send batch 0 through, and what we're going to do is we're going to do an easy backward pass. So we're going to do backward pass for the weights in this time step, and then we're going to do backward pass of the input, and then we're going to do backward pass of the weights. So remember, every single one of these is a single time step. So this does forward pass, backward pass of the input, backward pass of the weight. But since we already have the backward pass of the input, we can send whatever gradient this information has to the next GPU. So we can utilize this parallelism by making this do the backward pass on device 1 for the first batch. And then in the next step, we're going to do the backward pass of the weights. And since we have the gradient of the input and then the backward pass of the input. And then we're going to keep on doing this. And you can see here, the zeros are going to iterate like this. So this will be the backward pass of both the gradients and the weights. Down, 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 down here. So this is a single pass of our 10th batch. So 10th batch, it's the 10th batch, it's not the 0th batch, which goes from device 7 to device 0, and it does the backward pass from device 0 to device 7. So that means we do this forward pass and we update all the gradients doing the backward pass. Now while this is going, we have batch 11 running. So batch 11 is going to be running, and as batch 11 is running, we're going to have batch 12. Batch 12 will start here, batch 13 will start here, batch 14 will start here, 15, 16, and so on. So as you can see up here, this goes in the opposite direction. So we have batch 0 starting here, it goes down. So it goes from device 0 to device 7, so all these forward passes. It then does the backward passes, so it goes down here, and it iterates down backward passes. And you can see 1 is slightly offset. So once you get here, you enter this bottleneck. Am I going to do the 0 computations, or am I going to do the 1 computations? So 1 has to wait for this 0 computation to run going from the opposite stream. So you can see you get this massive mess, which I'm not going to talk about more because I think it's just optimizing via these units of time. So they define a unit of time as a forward pass, a backward pass for the inputs, and a backward pass of the weights. And I think they optimize this so that you minimize the amount of time it takes to do that. So you have this compaction strategy, and this compaction strategy should minimize how long it takes to do that. And they maximize the usage, or they minimize the time by also adding this second stream here. So hopefully that made sense. 2 streams going through. These streams have a unit of time for forward, 2 for backward, and you minimize that on these GPUs in some way. So you use a minimization algorithm that will create something like this. Having data going forward and backward at the same time, like if you just had data going forward, you would essentially use, like if we just had this doing the naive approach, you would do forward for batch 0, and then backward, you would end somewhere right here, and you would only have 1 batch that has gone through the entire pipeline. And in this case, you have, say, 6 batches that are in the pipeline going. So it's way more efficient to do something like this than do something like this than it is to do the naive strategy, which is one reason why I think this is how they maximize their compute. The strategy, how can we minimize the time of forward passes and backward passes in parallel? So they mention here it does pretty good compared to the other pipeline methods. But I think it's just how can you do this? Like minimize this using some strategy, some algorithm. So it's a lot of words to say that. Let's talk about the training framework, or rather the floating point 8 training. I think that is a training framework. So they mentioned some communication here. They mention you can minimize the memory, so you can recompute the RMS norm and MLA up projections to save more memory. You store a exponentially moving average on the CPU, and that way your model is less prone to noise. You want to use an exponentially moving average. Typically, the resulting model is better because it's less prone to noise in your data. And they mention after each training step they update it, which is weird. Usually you see that like it's updated, say, every 100 training steps, but here they mention they do it every training step, and you keep it on the CPU because it's just a weight storage. Shared embedding and output head for multi-token prediction. This one kind of confused me. They say with the dual pipe strategy, we deployed the shallowest layers and deepest layers of the model on the same PP rank. So I don't know if that's saying, I think that's saying you deploy shallow and deep layers on the same rank. But if you look up here, like the shallow layers have to be on either device 0 and the deep layers have to be on device 7 if you want to do this efficiently. So that was kind of confusing because you had, say, the shallow and deep layers on the same device, and you would start here, you would iterate to the end, but then you would have to jump back here to compute the deep layers. So that part was a little confusing for me, unless they were saying they hold the shallow layers on one PP rank and the deep layers on another PP rank, but then I don't think you're utilizing anything. Because I think what they're saying is, you have your input embedding here, your output embedding, and you have your transformer here. And this is going to have to go through another embedding layer. So since these are so close to each other, your unembedding layer and your embedding layer, you might as well store those on the same device. But I don't know how this ties into what they have up here, if you want to do that efficiently. Just something I wanted to note. This was kind of the only thing that was really, I was like, I don't even know. I don't know why. It kind of contradicts above. Floating point 8 training. So let's talk about that. That is, we'll go through this diagram. So mainly they do this mixed precision training for most things are a forward pass. Most things are just a weight matrix multiplication. And they mention that they do all this in floating point 8, but they store it in floating point 32. So they do this mixed precision training, and they do it in a really, really smart way, which is another reason why I think this is so efficient. So they start in floating point 8. Let's assume we have these master weights here. So these weights being updated. What we're going to do is we're going to store these in floating point 32. So we have these weights, but now we receive this input here, and we have these weights here, and we want to do a computation with them. So what you can do is you can just cast it to floating point 16 and do that, but that's slow. What we want to do is we want to do this in floating point 8. And floating point 8 should be twice as fast as a floating point 16 multiplication, theoretically. So what we do is we cast the weights to floating point 8, mentioned here, and we cast the input from B float 16 to floating point 8. So that's the first thing we do. Once these are casted, we do this multiplication. So it's a weight multiplication. So you have your multiplications, and you have your sum here. So you do the multiplications, and then you do your sum here to do your matrix multiplication, and you do your multiplication, your scalar multiplication here in floating point 8, and you do your sum. I'm going to talk more about this here, but you do your sum in floating point 8, and you store it in floating point 32. So all the operations are in floating point 8, which means it's faster, but you store it in floating point 32, which means you have the memory, or you have this accumulation size that is large enough to store large output values. So you should get the best of both worlds. You then cast your output to floating point 16, and you have your output, which can be sent to next layers. Once you're receiving a gradient from the previous layer, you do something very similar. So let's compute the two gradients. We have dgrad and we have wgrad that we need to compute. Wgrad is the weight gradient, dgrad is the input gradient. So let's compute the weight gradient. So for the weight gradient, we need our input here, and we need our weight here. So we take those two, and we cast them to floating point 8. So cast to floating point 8 for both the weight and the input again. You then do your multiplications, your scalar multiplications, and you do your sum. So it's the exact same thing. Wait, did I say you take your weight? No, you take your gradient, not your weight. Yeah, you take your gradient and you take your input here. You do the scalar multiplication in floating point 8, and you sum exactly the same. Where you do a sum in floating point 8, and you throw that into a floating point 32 bin. So you throw that in floating point 32 bin, and you get your weight gradient. Your weight gradient is in floating point 32. You then cast it, and you update your optimizer states, which then update your master weight. So same idea, doing the operations in floating point 8 and casting to floating point 32 to store them, and casting back to floating point 16 because that's what you do your operations in. They mention more about this over here and exactly what they do, but just know that they do the operations in low precision and they store things in higher precision. And then we do the exact same thing for dgrad, the input gradient, except we need the weight. So we take the weight, we cast it, we take the output gradient, we cast it here. So we cast those two, and we do the operations of floating point 8. We sum into a floating point 32 bin, and we cast that to be float 16, and this is sent to previous layers. So main idea is computation is in floating point 8, storage is in high precision. So that is the main idea for how do you make this thing a lot faster, and how do you make it stable? Because if you just do all floating point 8, this isn't going to be stable. This sum here is going to get overloaded, and it's going to run into problems. So yeah, floating point 8 computation, storage in high precision. So let's talk about how they do this floating point 8 precision. Like how do they actually put this? How do they put this in floating point 8? So this is a diagram here explaining how do they do this floating point 8 computation, which is it's as you would expect, floating point 8 using tiling. And I'll talk about the sum over here. They have tensor core versus CUDA core. I'm familiar with those. I'm familiar with them, but I don't know a ton about them, so I'm not going to be specific like, you compute this on tensor cores. It's something I am learning more about. I don't want to say something wrong with the tensor core versus CUDA core because I've used them, but it's not like, I program CUDA every day and I know exactly how these work. So they use tensor cores and CUDA cores. It looks like they use the tensor core for the multiplication, and they use the CUDA core for for doing collecting these multiplications here. And that's what I read as well, but I could be wrong. So first off, for a floating point 8 conversion, you have your inputs in floating point 16 here. So floating point 16, this is going to be a set of values. I think they call it NR. I could be wrong with that. It's in something. I'm going to call it NR. So maybe this is 128 values. And what we're going to do is we're going to quantize these. So we need to quantize these to floating point 8 somehow. Now, they use E4M3 mostly. So what this is saying is we have 4 exponents and 3 mantissa and that's how you want to cast it. So the amount of the amount of values, like the highest value you can store in here, is much, much lower than the values you can store here. So what you want to do is you want to reduce the size, but you don't just want to reduce the size, you want to reduce the size of a block, because if there are outliers, or if this block, like if you reduce the size block-wise, then this block is informed, like the quantization is usually a lot better, and the output or the accuracy is a lot better. Like if I had, say, a universal rule that was just divide by 127 or something like that, versus a rule that said divide by, say, the maximum value in here, the latter is much better than the former. So how do you do that? This is using the maximum algorithm. And the way you do that is by, let's take our floating point 16, let's get the exponent of it, and let's take the max exponent. So your floating point number is represented represented by the exponent and the mantissa, and you just take that exponent and you take the maximum exponent. And that's what we're going to store. Note that we have to store this value in a floating point 16 format, so we have to store it in the original format. This exponent here. Or actually, no, since we're using bfloat, we're using bfloat 16, so you just store the 8 bits. Bfloat 16 has 8 bits in the exponent, so all you have to do is store that. So I guess that would be 8, but it's just your 8 bits that you're storing for this. You then take your whatever maximum exponent that was, and you subtract off the maximum exponent in your floating point 8 format. So in this case, since we're doing E4M3, that would be 7 here. So exponent 7, because 2 to the 3 is 8 minus 1, which is 7. So that's what you have here. Then this is going to be our scale factor. So we're going to scale by that, and we're going to round it. And this basically puts it in the range of our E4M3 floating point 8 value, rather than it moves it from our floating point 16 range to our E4M3 range. And that'll be our int 8. And you do clamping for weird outlier values. So yes, this removes precision, but that's what you would expect. You would expect it to remove precision. And to reconstruct this, you just multiply by the negative. At least this is a very simple way to do this. There are much better ways. There are much better ways to do this. This is just a very, very simple way to do that. But basically, you're dividing by some value, but you're dividing by a value that is universal to a set of floating point values. So they mention over here, you have this scaling factor, and the scaling factor is like you have your input and you have your weight. So this is going to be our input here. So this will be of dimension, say like n by d, and this will be our weight here, which is going to be of shape, say d by d or something like that. And you tile your input by 1 by nc tiles, and you tile your weights by nc blocks. For each of these, you compute a scaling factor. So the scaling factor I mentioned below, so that would be here. So this is a scaling factor. And you then cast every single, you're casting these to floating point 8, as I mentioned above. So you need your scaling factors as you do your casting so you can cast back. And talk about that over here. So you take your inputs and you take your weights, and like I said above, you cast those to floating point 8. So you compute these scaling factors and you do the casting. Then once you've done the casting, you need to do your multiplication. So they mention here they have like the CUDA core, which is where you're going to put the high precision values. It's going to accumulate the high precision values, and you have this tensor core here, which does the multiplication part itself. So let's just look at one multiplication. This is our output matrix here. So in our output matrix, or rather, this is this is our output. So in this example, they look at just this one part here, just this one multiplication that you're doing. And they say on the tensor core, you take one tile here. So you take one tile, and you take one tile from your weights, and you just multiply them together. So we're doing this multiplication in floating point 8, and you sum them together, and you send that back to the CUDA core. So you do the casting to floating point 8, you store the scaling factors, and you do the computation, the matrix multiplication. So this is the multiplication and the summation. You send that back to the CUDA core, which receives the output of the matrix multiplication, and then it rescales it to floating point 16. So that's why you have your scaling factors here. So cast down, do the multiplication, cast up. This takes and this does the casting up here. Now they mention here, if you just do this naively and you just sum into this floating point 8 bin here, you just whenever you're doing this matrix multiplication, you do the multiplications and the sums. If you just keep on summing into a floating point 8 bin, you're going to run into problems. So what they mention is they do 128 sums, or they do some number of sums. So inner product here gives you a sum, and you keep on adding this to a floating point 8 vector, or to a floating point 8 output. So you keep adding to the floating point 8 output as you're doing these matrix multiplications, or as you're doing these inner products. So inner product, or partial inner product, you add that to your output, and this output is going to be represented in floating point 8 because we're doing floating point 8 arithmetic. But they mention after you do so many computations, the likelihood of you overloading this floating point 8 bin is quite high. So instead of just doing this for every, like you do this for every part of your matrix, like you just do the whole operation in floating point 8, what you do is you kind of checkpoint it. So you say, like, maybe after 128 values that you sum up in your vector, or in your inner product, you write to this output here. And this output here is going to be a floating point 32 register on your CUDA core. So your tensor core is doing your operations. It's doing your matrix multiplication, but you stop it in an intermediate step to take the output and you store it in this memory. So let's say you had, 512, a vector of size 512. Then you would do 128. You would sum that. You would do another 128 computations, and then sum that, write that back here to the floating point 32 value. You do it again and again. And this way, if, say, this ran out of precision and it was already overloaded, these values still, they matter. So this is way more precise because you are storing in a floating point 32 every now and then, as opposed to just accumulating in this floating point 8 storage. So that's what they mention here. To reiterate, basically every CUDA core, it's orchestrating all this computation for the matrix multiplication, and it's kind of receiving it's storing this floating point 32 information from the tensor cores doing the multiplications. For every multiplication, the tensor cores do a partial inner product. So partial inner product here, using the quantized formats that were created. So you quantize these from floating point 32 or bfloat 16 to floating point 8, and an intermediate product every time you do an intermediate product. So maybe 128, size 128, you will write that to the CUDA core. So you can store this in floating point 32 memory. You reset the sum that it is doing, and it'll continue for, say, another 128 times. And yeah, your output should be a lot more precise because it is storing in floating point 32 rather than in floating point 8. So that is that part there. Accumulating precision. So that was a lot. And those are the main things that they do using the compute that they have, optimizing the compute that they have. They first optimize the architecture, then they optimize the compute and the compute that they had. And these are the main ways that they do that. They have some more notes here. For example, they use E4M3 for all tensors. They don't need E5M2 for backward. So E5 would have a higher exponent. And intuitively, if you have a backward pass, since the backward pass is usually accumulating all these gradients, the magnitudes get quite high. So you would need a higher exponent to store higher values. They mentioned they don't need that, likely because of the quantization strategy, which is the tiling and blockwise strategy that I showed above, where you basically quantize it using a shared factor. And they mention that because you do that, you can stick with E4M3, and that means you have a higher precision within the window within the floating point 8. It's not larger, it's just higher within the bounds that it has because you have a higher mantissa. They quantize every block. They say we calculate the maximum absolute value online for each 1 by 128 activation tile. So 1 by 128 is what you do for your input, or 128 by 128 weight blocks. So that's what you do on your weight. You tile it in blockwise. And they say based on it, we derive a scaling factor and then quantize the activation or weight online into the floating point 8 format. So they quantize everything into floating point 8. Low precision storage and communication. They say compressing cached activations and optimizer states into low precision formats. So how do they do that? They say here, mainly bfloat 16 for the optimizer moments and floating point 32 for the master weights. So that's something to note. not everything is, and that was just what was shown above. They say we adopt the bfloat16 format instead of the floating point 32 format to track the first and second moments of atom W. They say without incurring observable performance degradation. I mean, that makes sense because bfloat16 can store quite a high precision. They say, however, the master weights stored by the optimizer and gradients used for batch size accumulation are still retained in floating point 32 to retain numerical stability. I'm guessing they found issues, so they had to do that. Low precision activation, they said it is a natural choice to cache activations in a floating point 8 format for the backward pass in the linear operation, or for the linear operator. However, special considerations are taken on several operators for low cost, high precision training. So like there are a few things you can't store in floating point 8 because it runs into problems. So they say inputs of the linear after the attention operator. They say here that these activations are also used in the backward pass of the attention operator, which makes it sensitive to precision. We adopt a customized E5M6 data format exclusively for these activations. So like the attention operation itself, like it uses the exponentials. So you usually need high precision for the attention activations themselves. So they mention here that they do that here. They do E5M6, not E5M3, which is an interesting format. What is that? 6. That's a 12. Yeah, that's 12 bits. So that's got to be really annoying to do computations with. So that's that. It's somewhere between floating point 16 and floating point 8. So I mean, there you go. If you want to code floating point 12, go ahead. Inputs of the Swidelu operator in most. So to further reduce the memory cost, we cache the inputs of the Swidelu operation and recompute it. So they basically checkpoint Swidelu. Low precision communication. Yeah, not a big deal. So that is mainly, and they have a lot of suggestions here for if you're actually building it. I'm not going to talk through those. I mean, I read through it, and I'm not going to talk through it because unless you are training this on a massive cluster, it doesn't really matter. All right, pre-training. Now I can finally talk about training, which it isn't too long. So pre-training and data construction. They mention here how they do this fill in the middle strategy. So fill in the middle strategy does not compromise next token prediction while enabling the model to accurately predict middle text based off contextual clues. So they train it to also do text editing within the middle of text. So as you can see here, which is quite nice. That means it can do like code editing and stuff. And they mention it doesn't have degradation of the next token prediction. So that's cool. Some interesting notes with the hyperparameters. They say each MO layer consists of one shared expert and 256 routed experts. So almost no shared experts. Where the intermediate hidden dimension of each expert is 2048. They mention here, among the routed experts, 8 experts, so k is equal to 8, will be activated for each token, and each token will be ensured to be sent to at most 4 nodes. So that's what was mentioned before. You don't want to send all these experts all over the places because of communication, like the communication issues that you get with that. It'll be a lot slower. The multi-token prediction depth D is set to 1, so they just do next token prediction. Besides the exact next token, each token will predict 1 additional token. So they train this on an initial sequence length of 4K. Here, they show that it does pretty good on Needle in a Haystack. It gets awesome scores. I mean, that's what you would expect because it doesn't use like linear attention or anything, so it should be good at that. But this is on the extended length. So they initially pre-train on somewhere around here. So the extension length is pretty good, or the length extension, long context extension. They say here, after the pre-training stage, we apply yarn. That's what they do. And they only apply that to the K part, which is the decoupled part that I mentioned above, for context extension, and perform 2 additional training phases, each comprising 1,000 steps to progressively expand the context window from 4K to 32K, and then from 32K to 128K. Oh, never mind. The initial context window is there. So obviously it works pretty well. And the first phase, sequence length, is set to 32K. So first long context extension, and the batch is set to 1920. So they increase the batch, or they decrease the batch and increase the sequence length. During the second phase, the sequence length is increased to 128K, and the batch size is reduced to 480, and the learning rate is static at something low. They have some evaluation benchmarks. It does good overall, as you would expect. And there are some interesting ablations here. So what is this ablation? This is ablation studies for multi-token prediction. So I found this one really interesting. This is no multi-token prediction. This is with multi-token prediction. So just one token that you're predicting. All you have to do is add a single transformer layer, and it does a lot better on some of these tasks. Like, look, MMLU, it goes from 50 to 53. Like, that's a significant jump, at least 20 to 26. At least for however much a benchmark says. You can squeeze, you're using the same amount of data, and you can squeeze a lot more performance out of your model by just adding another token that you're predicting. Even though you're not using that to speed up your model during inference, it helps you in the end with accuracy. So normal loss. This is auxiliary loss function. So like I mentioned with Mo, if you usually do this loss function optimization, like you add an additional loss function, and they have this auxiliary free loss function, and they show that overall the model does better if you have this loss function, this loss free auxiliary thing. So if you instead of use the rule that they have where you increase the scores, rather than using a loss function, it does better. And that makes sense because the model doesn't spend any time optimizing the second loss function. It only has to optimize the next token prediction, and you're manipulating the model to use certain experts. So that's cool. They mention here the key distinction between auxiliary loss free balancing and sequence-wise auxiliary loss lies in their balancing scope, batch-wise versus sequence-wise. Compared with sequence-wise auxiliary loss, batch-wise balancing imposes more flexible constraint, as it does not enforce in-domain balance to each sequence. And they say, we observe that the auxiliary loss-free model demonstrates greater expert specialization. And we can see down here, if we look, here is a normal model, here is a normal model with the loss functions. These are loss-free. You can see there's higher expert loads, which means that there are experts that are specialized. While here you can kind of see a smoothing between all experts where almost like all the experts are kind of utilized the same. So this is what you want. You want specialization. You just don't want over specialization. And that's what it seems like you get here with their thing. All right, R1. So I don't want to go through R1. It's mainly it's mainly this PPO part. And there's a lot of videos on it, like Yannick's video is really good on R1. I do want to talk about it a little, like I want to mention a few things, but I don't want to talk about what they do. But I mean, basically, the main thing it falls, like I think one of the biggest things is instead of using a reward model that learns whatever task you want it to learn, it is better to use a rule-based model because a neural reward model will run into reward hacking. And that's problematic because the model doesn't learn what you want it to learn. Instead, if you are able to have a rule-based approach, you should use that. So, for example, like math, I can say, math, you are right or you are wrong. That is a really easy rule to have. So I don't need a neural model for that. So use that instead of a neural model because it cannot be reward hacked. You can't reward hack that. So that's what they have here. But if you don't have that, then you have to default to using a neural model. So it's no different than what you would normally have. So that's one thing with R1. Like if you have a reward model, like if you don't have to use a reward model, don't do it. This here, GRPO, it's like a changed PPO. Like I said, I don't want to talk about it because others have talked about it much better than I can probably go through it. For example, Yannick's video is really good. But I do want to mention something. So like there's all this hype around GRPO. Oh, it's going to change, like reinforcement learning is coming back. I disagree. So I don't think R1 is necessarily good because of the RL itself. So like, sure, you're applying the reinforcement learning to it, but I don't think it's good necessarily because of that. Like the model is already good at it's already good at exploration. It's trained to do that. It's kind of good at exploration. Rather, I think like this reinforcement learning part is like it emphasizes the trajectories that make it think longer. But it already knows how to explore the space it's put in. So rather than everyone jumping on RL, remember how RL like is usually like if I have a cart pull model or something simple like that. Just remember it first has to learn to navigate the space. The model, the LLM, it already knows how to navigate the space. So putting RL on it isn't like it doesn't have to do the exploration as much as it would if it was like a cold initialization model. Like the LLM is good at that, but a cold start, like if you had a cold start LLM and you applied this to it, it wouldn't work at all. It would be complete garbage. So GRPO, I don't think is really anything, like I think it's cool, but I don't think it's super special. It's similar to PPO. But I don't think everyone should start hopping on the reinforcement learning train because it's going to run into the same problems as you did before. This exploration problem and having a model start from nothing going to something. I think the reason this works so well is because the model already knows a lot. It already knows a lot about the task you're putting it on, and reinforcement learning it just helps. It emphasizes some of these long trajectories. So that's the note I want to make about this and R1. But yeah, that is a long paper. And yeah, that is DeepSeek-V3. There you go. Yeah, we'll see where this goes. I think it is cool. I think it is interesting. I do think it's overhyped. But I do think that the paper is really cool and they have a lot of really cool details in here. So yeah, that is that. Yep. DeepSeek.